So the current will follow by certain phases difference from voltage. This is your voltage. Voltage at input or voltage at output, you will have the same pattern actually. It will not distorted, but if you run through the rectifier, so you will see only the positive cycle. Positive, then it will diminish or it will be void, and also on the next cycle positive as well. But in terms of current it will be delayed. And first, initial it start at 0 because it has no current that flows inside the circuit at the first place. So it will be delayed from 0, and even though the voltage already crossing the 0 reference, turn into negative cycles, the current still available in the circuit. Means that in the inductor, okay, it will delay, it will diminish into 0. Then only at that time, it will start at next cycle from 0 as well, and delay again. And this is the voltage that measured inside the inductor. And this is the input, inductor current and inductor voltage. Positive cycle, then down to 0, then it conducts in another voltage, what so-called polar pole. Okay, at the first place, if you take a look at your circuit here, we plot the phase from 0 to pi, and this is in the what's so called in frequency domain, in time domain, sorry. From 0 to pi means that 0 to 180 degrees, then from 180 degrees to extinction angle. Beta is extinction angle, means that when the current cross 0 crossing, then from extinction angle up to the full cycle of 2 pi and 360 degree. Okay, from 0 to pi means that from 0 to pi here. This is 2 pi, kan? One full cycle. From 0, this is pi, this is 2 pi, this is another cycle. So from 0 to pi, how much the current? Means that where or how the current flows. It flows in positive and positive. So it flows in positive, and the diode is blocking. Flows in the positive cycle, or in terms of clockwise and clockwise cycle. 0 to pi. Then it continues. Actually, it continues from pi to beta for current. 0 to pi, and it continues from pi to beta, means from pi to extinction angle. Then only after pi, it will block. The current already enter the 0 region or cross the 0 crossing. So at that time, current is 0, but voltage will be blocked and will be blocked. Yeah. So if you take a look at this snapshot of the curve, this is the input. This is the input voltage of the system. Meanwhile, this is the current that flows into the load. So we are dealing with the RL load. So this is the current that flows into the load. We have a certain delay angle, what's so called a firing angle or delay angle. So this is alpha is a firing angle or delay angle. Meanwhile, your beta here from 0 to where the current return to 0 is so-called extinction angle, and whereby the current extinct. And the amount or the values of where the current rise up to where the current turn to 0 is so-called conduction angle. Conduction angle. Okay. Theta here represent the maximum position or magnitude of your current. Okay. So this is the 4 attributes or elements or parameters that are important for you all to take note or to observe. Okay, the values we might gain or we might able to get from calculation, or we can get from the PE curve that I asked you to download and print. Because in power electronics, we are not going to memorize. That's not the main what's so-called focus. We not ask you to memorize all the formulas, but it's more important for you all to get to know where to get the reference of the formula and make use of it to put into your system. Because you are going to build the system of power processing computer, and you're not going to memorize all the formulas. That's why we expose you all to the simulation tools. In books, if you take a look in books of your Daniel William Hart electronics, they use PSpice, but in our lab we use PSIM, and you are open to use LTSpice or MATLAB. Means that you are able to use any tools to get the parameters and to obtain the parameters value. Okay, the most important is that you know how to what to expect and where to get the answers. Okay. Okay, this is the source resistor voltage, inductor voltage when we design a circuit. So we put a probe here, probe at your source, probe at your diode device, the probe voltage probe across your resistor and also across your inductor. So here are the result. In terms of voltage, usually we proceed in lab to expose you all to the real situation of the real world circuit. You have to bear in mind, when you want to measure voltage, measurement is taken place by you putting your probe across the terminal of the device. Let's say you are probing your source, so in between the positive and negative terminal of your source. If you are probing, if you are probing your device, so from anode to cathode of your device, if you are probing your voltage response of your load, so in the positive, negative of your terminal as well. But if you going to measure the current, so means that you have to put in between the lines. Means that you cut the wires, you put your ammeter, then you connect to the another terminals that you have cut. Okay. So you have to bear in mind, because this is either, even though this is a simple methods, but seldomly you forgot to most of you lah, sometimes you forgot to be alert on that, so you mistakenly connect, and the result that you get is not what we expect lah. Okay, in terms of curve that you might have or you expect to get, so in terms of voltage, we shall have a pure sine wave, which indicate or composed of maximum magnitude of voltage, sine omega t. And in terms of current, waveform of current, it's affected by the angle of beta here, excitation angle. And this is uncontrolled converter. So we don't have any element of alpha, but we have the beta, the extension. Means that the higher the L, means that the inductance that involve or exist inside your load, so the higher or the longer the beta will be. Okay. So this is the parameter or the formulas that usually involved inside your calculation or inside your determination to find the element of impedance, output RMS current value, output average current value. So voltage is the pure sine wave. Meanwhile, your current only exists on the positive cycle of your system. Positive cycle, you have this pattern, Bm divided by impedance. And when it has enter the beta extension angle up to full cycle 2 pi, so it will be diminished to 0. Okay, your impedance consists of element of resistive squared plus the effect of your frequency omega L in Newton value squared. So this is the theta now is the load angle. Theta is your load angle. The higher the L, the higher the load angle will be. The highest is 90 degrees. The lowest means that if there is no element of L, the only remains element is R. So arc tangent 0 over R means that arc tangent 0. So it become 1. So tau is your ratio of L over R. How much L compared to R on that load element. So RMS current represented by this formula and average. Why we need to calculate RMS and average? Because when we want to select for the switch or the components that we want to put or we want to justify for your device here, this is your converter. This is the device that you have to put in place. Let's say you are providing, you have an input of 240 volt. You want to provide only 5 volt to charge your handphone. So the device is small signal device, not so big. But if you are providing, you are charging or you are putting the load in terms of watts, hundreds of watts. So the device, we have to you have to select the bigger size of device, bigger capability or capacity of the current capacity of the device. So how big and how high the current capacity, so it depends on the RMS and average. That indicates inside your data sheet later. Okay, we have discussed this one, I think. And I have upload to the YouTube, and I shared you the link. Is it this one? Already is it? Or have not yet? Oh, this one have not. Okay, for example, this one is available inside your reference books, page 71, actually. Page 71. Okay, let's say we have this scenario whereby we have a source of 100 volt maximum, peak voltage of 100 volt, sine wave. And we have diode, we have element of R and L, element here, of 100 ohm and 0.1 Henry. So determine expression of the current in this circuit. Means that what are the current pattern of the circuit when we put in all the exact or the real values here into the scenario. So this is the expression of your current. Voltage is just a simple or a normal sine wave. This is the current. Is that it involves the maximum voltage that exists inside your circuit divided by impedance. So the most important is that when you get this kind of scenario, what are the theta load angle and what are the tau here? Then it become more easier for you all to find out the next parameter that highlighted inside the list. So the expression of the current, the average current, RMS current, and the power absorbed by the RL load and the power factor. Okay, if I explain here, it will take time. I will summarize inside screencast-o-matic later, and we upload the discussion on this. So we discuss the theory first inside within this class session. Okay, you give a try, or you can refer to your textbook. And by the way, inside your textbook, they calculate in terms of RMS current and average current using formula, and you have to iterate either using your calculator or you can key in inside your laptop to find out the value. And in terms of beta, we have two options, like what I asked you all to download the PE curve. So the PE curve already indicate what are the expected beta. It's not going to be exactly the values up to certain decimal number or whatsoever, but it's just a prediction or what so-called range. Range. I show you the PE curve. Wait, huh? If you take a look at your PE curve, can you see the PE curve? Electronics waveform analysis performance curve. So this is for control rectification. Actually, the diode and SCR almost the same, their response. So means that if you use SCR, you are able to control the triggering or alpha angle here. But if you use diode, so the alpha will be automatically at 0. Means that it will conduct once the forward bias curve. Okay, alpha represent your triggering angle. For diode means that your alpha is 0 lah. And your alpha is 0. And our concern now is on the beta, which is the extinction angle. Okay, once you get this kind of circuit, the most important parameters that you have to calculate upfront is your impedance, which is Z, which combines the element of resistive plus inductive with the effect of your frequency. And If you have a 50 hertz, so j omega l omega is equal to 2 pi 50. If your frequency is 60, so 2 pi 60 L squared plus R squared, so that's your impedance. And also your load angle. Sometimes written as phi here, sometimes written as theta. So both are the same load angle. Okay, when you take a look at your curve here, you can see alpha and your delta. Okay, alpha is from 0 to 180 degrees. Why you cannot trigger more than 180 degrees? And so we'll take a look at that one later. So this is the amount of alpha. Means that if you trigger at the first point, it was 0. And the highest is 180. Means that it only can be triggered from 0 to half cycle. This is the positive cycle. Yeah? After 180, it enters already a negative cycle. It's no mean. And you cannot trigger it already. Okay, for diode means that your alpha is 0. Alpha is 0. And okay, at load angle of phi or theta is equal to 0 means that your element of L is the lowest. Lowest means that you have the element of R. So if element of R exists, means that if you trigger at 0, you will have your extension angle is 180 degree. This is the element of L, whereby the L of LR 0 and the remaining element is R, and pure resistive load. So this is the curve that you can follow, the lowest curve. Means that if you have a SCR, you trigger at 0, extension angle will be 180. If you trigger at 20, so your extension angle will be 160. If you trigger at 90 degree, your extension angle will be 90. You trigger further up to 180 degrees, your extension angle will be reduced as well. Okay, this happens when your resistive load only available inside your load. But when you have a more inductive load or more inductive element exists inside your load, so the above curve apply. Let's say the highest curve means that only element of inductive dominates inside the circuit. The higher the alpha you trigger, means that the longer the alpha you apply. So this is the curve. Let's say if you trigger at 90 degree, for 90 degree for pure resistive, it will diminish at 90. But at 90 degree, at pure inductive load, will diminish at 180. So this is the difference between the extension angle that exists when the element of your R and L change. So the load angle change, so the curve also change. So you will understand better if we proceed, once we proceed with the example later. Okay, we go back to the notes. Just now it's uncontrolled, now it's a controlled half wave. Means that just now we use diode, now we are going to use a SCR, silicon control rectifier. So the same, we probe all the voltage across the source terminal, voltage load terminal, resistive, inductive, and diode. So now the analysis will take place between 0 to alpha, then alpha to half cycle of your pi, of your circuit, of your full cycle of 2 pi. Kan? So we from alpha to pi, then up pi to the extinction angle, and extinction angle to full cycle of 2 pi. Okay, what happened now is that from 0 to alpha, so the current flows 0 to alpha, the current cannot flow because we have not triggered yet the alpha. So the discontinued dot here means that there is no current flows inside the circuit. And 0 to alpha, no current flow. Once we trigger, so only the current will flow into your R and L. Then it will continue to flow up to beta. And once continue, once reach beta, only then the current diminish to 0. Then from beta to 2 pi, the current stop. So that's for current point of view. In terms of voltage, we have a blocking voltage from alpha 0 to alpha. And the voltage will increase from 0 to certain value when enters the alpha to pi. Take a look here. So this is the input voltage from 0 to alpha here, 0 to alpha, alpha to pi here, pi to beta, extinction angle from beta to 2 pi of full cycle. So from a current point of view, this is the current curve. Only it will trigger at alpha. You will have your current flows up to theta of maximum value or magnitude, and it will reduce and reduce again down to beta of extinction angle. Meanwhile, your blocking diode will blocks. So actually, this is the curve of your load, and you will see your load. This is a V resistor and at resistor, because inductor it is storage element, so we measure at resistor point of view. So we shall see a voltage appear only at alpha, and it will reduce. And once your source enters next cycle, there will be still a voltage that flow block inside the circuit, and down to when the current enters 0 or next cycle. So this is the pattern of current, this is pattern of voltage. So this is the same. Alpha, triggering angle or firing angle. Beta is your extinction angle. So this is inductor voltage. Resistor voltage, inductor voltage. This is the switch voltage. If you probe at the switch, so this is the pattern or the voltage that you can see from your switch point of view. So load current and load voltage. So the load voltage is the sum of your inductor voltage plus the resistor voltage. So here are the formula of the pattern that you able to see or generate from your circuit. Okay, we have a source of pure sine. Meanwhile, we have output voltage with the modified curve based on how much alpha applied and how much the beta that result by the alpha. So we have this curve represented by this formula. It happens only from 0 to 0, actually from alpha to beta here, and 0 happen at otherwise. No? So this is the average current output, average RMS current output. You will integrate between alpha to beta. Okay, this is example. Same previous uncontrolled with a load. So we shall discuss this one inside your pre-record lecture that I will upload later. But if you want to solve or do exercise upfront, you can refer to page 98. Page 98. So the summary, we have gone through or we have discussed regarding uncontrolled half wave and also control half wave rectifier with a load. Okay. Okay, next is your any question from the floor? Any question?
No, Doctor.
No. Okay, if not, we proceed with next slide of half wave rectifier with a freewheeling diode. Okay, just now we have a circuit with the element, device, resistor, and inductor, and source. Now we include freewheeling diode. Means that if you have ever learned the signal and systems or in the device, we have learned that the resistor is a load, but inductor actually is a storage element. It's not the load actually, and because it's not consume any power. So what happens that when we switch off at the first place just now with the circuit, we don't have this freewheeling diode. We switch off the source, there still will be current that flows inside the inductor. So where the current will flow, if we don't have freewheeling diode here, it will return back to the source, and the current will return back to the source. So you shall have a issue whereby you have to delay the turn on the next cycle if the inductor value is high. Means that if you switch on your circuit when there's still current inside the circuit, so there will be a backfire. And layman said backfire. Means that you have a spike and will have a reverse energy to the circuit and will burn your circuit. So what happens that you have to make sure that the current inside the circuit is returned to zero. Only then you can switch on the next cycle of switching. So to assist the circuit such that the current inside the inductor return to zero faster, so what happens that we provide the freewheeling diode such that the remaining current can flow back to the circuit and diminish earlier. Okay, we have here when we switch on the circuit, so the current, this is the first phase, this is second phase. We switch on the circuit, the current will flow from source to load, from source to the load. Then when we switch off the source, so switch off and switch off, there's no current or no voltage being applied, so V equal to 0. There's still a current that flows into the inductor. So what happens that the flowing current will return back to the circuit through the freewheeling diode. Can you see my screen?
Yes.
Sorry, give me 1 minute. I'm looking for my time. Okay, so far, is there any question from the floor? Any concern? Or you want to take 5 first? So guys, we take 5 first, 5 minutes. Okay, can we continue?
Boleh Doktor.
Okay. Okay, if you take a look at this circuit, so the first thing is that when the first cycle happen, okay, this is your source. So this is the expected rectification cycle at your load. Okay, the first cycle happen when we have a voltage source of positive, negative during positive cycle here. So the current will flow. The current will flow in. So this is the first cycle of current flows when we have source applied to the load. So V out is equal to V source. V out measured here means that positive, negative of V out is the same as positive, negative of your source. So what happens that when V out is 0, means that when V out is 0, when it enters the negative region here, means that your output is 0. This is V out. Is V in or Vs. So V out is 0. When V out is 0, so here are the diode actually. When you conduct forward bias, the diode is short circuit. Short circuit means that conducts full. Here is as well your diode here. When it enters a negative cycle, the remaining current that remain inside your inductor here, it will become a source actually, because inductor is a storage device. Just now when you flows in, the inductor is positive, negative polar poles. But when the source is taken out, so means that the flows of current that will remain inside your inductor, we have to flows out, but it flows into the diode, which is conducted when you forward bias. Just now the current flows from here, it cannot enter the diode because it's a reverse bias, so it goes into the load, back to the source. When you taken out your load, taken out your source, there's remaining current inside your inductor, it has to flow. And because this is short circuit when forward bias, so it flows here back to R until down to 0. And so this is the first cycle, this is second cycle. Go into diode, back to R, and until the current down to 0. So that's why I explain here. Positive source voltage Vs equal bigger than 0. Positive cycle just now. D1 on, D2 off. So figure B represent the equivalent circuit, and the voltage across RL load is the same as the source. Then when your source enter negative region, negative phase, D1 is off, D2 is on. The equivalent circuit represented by figure C. So the voltage across RL load is 0 actually at that time. There's no voltage, but there's remaining current that flows out to the circuit. Okay, since the voltage across RL load is the same as the source voltage, when the source is positive, and 0 when the source is negative. The load voltage is a half wave rectifier, rectified sine wave. So this is what you expect to see from a load point of view. And load point of view is that load point of view lah, when we probe between positive of R and N of L. So this is what we expect to see. It has a conduction positive, then it blocks. It has conduction of positive and it blocks, positive and it blocks. It repeats every cycle. So this is for voltage. What about current? So the current, sorry. When the first the energy, the first at the first place, the energy, the circuit is energized. The load current is 0 and cannot change instantaneously, because by right, when at steady state means that after it runs a long time or certain period, it becomes stabilized already. So that's so-called steady state. That's why when we expect you all to run your simulations, you cannot probe or you cannot calculate. You cannot include this transient part, because, and also you cannot run in a duration that is so short, because it will not represent the whole what so-called steady state response of your device, of your system. And so your T1 and T2 or T starting and Tn here, by right, should only take the steady state region. And even though we ask you all to just present out your result in 2 cycles, so that 2 cycles by right you take on the steady state region, not on the starting or transient here. Okay, is that one of the concern? Okay, when the circuit is firstly energized, it starts from 0 lah. That's why when you see that when you start your simulation, the curve will rise up, and after certain time only it will become stabilized, because it reached steady state. So the current reach predict state after a few periods depending on the R time constant. Is that the higher RL you have, the longer it takes, because it needs to charge your L, and longer time it takes to stabilize, the higher the L. And if R, it just responds directly now. But if you have element of L, inductor, the higher the inductance value ratio, so the longer the steady state going to reach now. Okay, this is steady state load lah. Actually, this is a steady state load. After you run a certain time, you will have the steady state. The average current will be seen here. Okay, if you run at the first place, it start from here actually. Start from 0, increase, swing, then stabilize after certain period. This is steady state current. Okay, for diode 1 current, this is diode 2 current. So when you switch on, the current will rise up slowly because of element of inductor. It needs times to charge the inductor. It does not follow the voltage here, but it delays. It has a delay. Then after the voltage is taken out already, so you cannot see any current in diode 1, but it returns to diode 2. Means that the current flows down, it rise up, and when you take a look at diode 2, you can see that it going down, and the current absorbed by the resistor, and it rises up here. When it down here, absorbed by resistor linearly. So that's why you can see the linear decrement here down to full cycle. Then when the next cycle starts, it starts again, rise up gradually. merely sine wave pattern and reduce in the linear curve. And so the sum of your output will be like this. This is more to sine curve. This is more to linear curve. Sine, linear, sine, linear. This is output. This is the current that you can see from diode 1, from diode 2 separately. This is the element of current that you can see from output of RL. Okay, in terms of formula, voltage of this pattern represented by this formula. Meanwhile, your impedance and your RMS. So this is RMS current. It consists of all the element of fundamental element, harmonics, first harmonic, second harmonic, third harmonic, fifth harmonic, first, second, fourth, sixth harmonic, and the elements of harmonic. We shall see the harmonics elements later, but means that the RMS current is consists of all the harmonic components of your sine wave. Okay, example, this one is referring to page number, I'm not sure this one, we'll check later. Inside the book as well, 100 something I think. Determine the average load current, voltage, and the power absorbed by the resistor of the circuit, where the current, the resistor is 2 ohm, inductor is 25 millihenry, maximum voltage 100 volt, and the frequency is 60 Hz. So please bear in mind when you use calculator, the calculation here they use in radian. Meanwhile, your PE curve is represented in degree. So you have to be careful, be alert. Once, sometimes you need to have a calculation or setting in radian. Sometimes you have to convert into degree. So radian in degree, just convert by, if you have radian, you want to go to degree, you just multiple by 180 divided by pi. So you get in degree. Okay. If you want to convert into radian, just times pi divided by 180. So we have come to the end of this uncontrolled half-wave rectifier with IR load and freewheeling diode. So I think we have end the session now. I will upload and compose and upload the exercise, and we pick up any exercise from the book that is suitable for our chapter, and I will upload to the portal and we will advise you all, info you all later. Meanwhile, if you have any concern, any question, you can ask me right now. You can write inside the chat box, or you can ask me directly. Is there any question?
Sir, yang uncontrolled ni tak pakai PE curve?
Uncontrolled, kalau kita nak cari dia punya, if you want to take find dia punya beta, still we have to use the PE curve. The PE curve actually, wait ah. Okay, if you can see the PE curve that okay, this PE curve is used to find the extension angle. By right, we can use calculation, but for our purpose of designing the converter, we are focusing or we are stressing more on the system, and we are not going to actually express on the how to memorize and how to extract, and we more focus on the system. Means that what are the expected range of excitation angle, and then the information will be used further for our determination of circuit device, the size, the value or the setting of our input or setting or limitation of our output, our range of our circuit. And so PE curve can be used as a tool, and you can use calculation if you convince or confident with calculation, or you can use PE curve because we just need to obtain the excitation angle. So this is the range of excitation angle on certain load angle, because when we involve RL, okay, RL, as I mentioned to you all, so first thing we need to do is that we have to acknowledge on the impedance. So impedance consists of R and L element, and so you have value of R, you have value of L, so you find out what is your Z and what is your load angle. So Z, the impedance, and load angle will be used inside your calculation later. And this load angle is important for you all to determine your extinction angle. So this is load angle. Load angle of 0, 15, 30, 45, and the maximum load angle can be obtained is your 90 degree, from 0 to 90 degree. This is the highest inductance element. This is the when the resistor dominates, load angle will be 0. When inductance dominates, the load angle will be around 90. So different load angle will represent or will emit or will produce different excitation angle. And this excitation angle also later on will determine how much your safe alpha you want to set. And that one kita akan discuss later. Okay, let's say if you have a load angle in between, because this is the generic number of values. Let's say you have load angle of 20. We don't have the curve here, is it? So what you need to do is that you just draw the intermediate curve in between 15 and 30. So it will be no problem. And you just estimate in between 15 and 30 here. Or let's say you have a 20 degree of load angle. So you draw your own curve in between here. So when you set at alpha a certain value, so what is the expected excitation angle you have here? Or later, if you want to have an excitation angle of certain value, what are the expected alpha you need to trigger? Okay. And this excitation angle and alpha here is important for you all to determine in terms of when you have certain input of certain voltage, you want to get certain voltage of output. But when the input deviate from the spec, so what adjustment of alpha you need to apply to your circuit? So this PE curve is important for your reference. Okay. So this is the PE curve for half-wave rectifier. To find out the excitation angle based on triggering or firing angle. This is actually the magnitude of IM, maximum theta here. Not yet being used here, but you can refer. This is when we adjust the alpha, what will happen to your, in terms of maximum SCR current. So I SCR maximum here equal to I max nominal, normalized. Normalized ni per kali. And so called constant bukan constant. V peak divided by impedance Z times IM maximum normalized. So IM normalized here, I maximum normalized is depending on your load angle as well. Pure resistive load, higher inductive load, highest inductive load. So you will get different I maximum normalized. you put inside your formula here. So it will determine what is the maximum ISR current that will be exist inside the system. So where we want to use this ISR maximum? ISR maximum is a reference for you all to select your SCR, silicon control rectifier from manufacturer. You want to design your circuit, you have to buy your device or your SCR or your diode or your MOSFET. So this is determine what are the spec of the diode or the SCR that you need to buy. If you buy lower spec, so once you put inside a circuit, your circuit will be blown, and your device actually will be blown. Okay, because this is important to find out, to make sure that your system or your design that you design and you fabricate, you market to the market will withstand at least up to the warranty period of your product lah. Okay. Any question from the floor? Any other question?
Ada.
Ada lagi. So your lab, you proceed with your OEL, and the template of your OEL is, I think, already uploaded, attached to the portal. To Google Classroom, you can refer to the
Ambil yang Dr. Ahmad Afif ni kan?
yeah, the same template. Actually, just a technical paper template you can get anywhere, but IEEE templates lah. We have a double column template text, double column text template lah. Font, I think around 9 or 8 like that. You check again. Okay, if there's no other question, so next week we shall discuss the full wave rectifier with resistive load and full wave rectifier lah, resistive and inductive load and all of that. Consists of, I think, how many pages? Oh, 40 pages. Okay, next week we shall discuss the full wave rectifier, and your test will be after your break, after raya lah. So as I told you before, test 1 will be in full wave rectifier lah. So on the AC/DC rectifier parts lah. Okay, that's all for today, I think. Is there any question? No more. If no, we shall dismiss. Please key in your attendance to the link that I provide to the chat box just now. Okay. If you have any question, you can ask me through WhatsApp. We shall discuss.
Cik,
ya.
Yang buku tu mana nak dapat
Oh, buku reference ni lah. Nanti I check balik sebab buku ni saya dah lama dapat ni, saya tak pasti dia punya supplier siapa.
Oh, tak ada bentuk dalam.
Cuba tengok dekat Shopee kalau ada.
Oh, dalam Shopee.
Kalau dekat rumah better you buy from Shopee lah, dia akan post directly. Kalau dekat sini saya boleh cari supplier, dia akan hantar sini, dia boleh ambil kat Shopee office lah. Tapi kalau dekat rumah, dekat mana?
Nanti cik hantar gambar depan ni lah, cover page dia.
Tengok ni, nampak?
Abu cik.
Tak nampak ah?
Tak nampak.
Tak apa, saya nanti saya paste dia punya ni.
Okay, alright.
Beri dekat WhatsApp nanti.
Okay, terima kasih.
Okay, if there's no more questions, so we shall dismiss the class. Thank you very much for your attention. Okay, see you again. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum.